In section 3, we're going to be continuing the conversations from section 2, where we're going to start talking about function analysis from a graph. So section 2 was all about graphing functions. We graphed a whole host of parent functions, so you should have all of these shapes floating around in your head that functions can be. But those are not all of the different shapes. There are other shapes out there, and we will certainly show more of them as the semester goes on, but those will be the basic ones that we need here at the beginning of the semester. And we also looked at how to take those and turn them into piecewise functions, which is still something that we ended up doing graphing with. So I want to continue with that graphing theme and start giving you some other pictures and ask you to be able to answer questions by extracting information from the graph. So example 3.1 is going to do just that. It says the graph of a function t gives the temperature between noon and 6 p.m. at a certain weather station. Use the graph of t to approximate the answers for each part. So one thing that strikes me is certainly the word temperature, and then it says between noon and 6 p.m. So as I look at my graph, I need to make sure that I understand what the horizontal and vertical axis represent in order for me to be able to answer any questions that might come up. So my understanding here would be that the horizontal axis is here to represent time. So for example, 4 would represent 4 p.m. 1 would represent 1 p.m. and the others would follow suit, but the one that doesn't fit that same profile would be 0. There is no 0 p.m., so 0 is going to have to be used to represent noon. But that would take care of the times that I think we're going to need. And then on the vertical axis, we have starting at 0 going all the way to 40. So this is going to represent temperature values. Let's take a look at part A. We're supposed to be finding two things, t of 1, t of 3, and t of 5. So these are examples of function notation. I want to know what is the temperature at time 1. So I'm not really looking just at the 1, I want to know what's the temperature at 1. So coming over here to where I see 1, if I carry that up to the curve, I will eventually find a point that I can associate with time 1. And then I can go horizontally from this point until I get over to the vertical axis, at which time I can see that I have a value somewhere between 25 and 30. Now with the graph, the best that we can do is just approximate. And it says here to approximate the answers. If I had the equation, I could calculate more exactly what I was supposed to be getting. But with the graph, approximations will be fine. So I can say that t of 1 is approximately, we'll say about 27. If you say 28 or 27.5, those would be fine as well. And then we'll do the same thing for t of 3 as well as for t of 5. T of 3, I'll come over here and take a look. Here's 3. I can carry that straight up. And if I look over to the left, it might be about 31. So t of 3 is approximately 31. And t of 5, there's 5. Looks like I'm going to be just a little bit underneath 20. So we'll call that maybe 19. So t of 5 is approximately 19. Moving on to part B. Which is larger, t of 2 or t of 4? Now if you don't understand function notation, then you might think, well, this is obvious. 4 is certainly going to be bigger than 2. But that's not what we're asking for. We're supposed to be comparing t of 2 with t of 4. In other words, the temperature at 2 compared to the temperature at 4. So really this is just a continuation of what we did in part A. if I want to look at 2 o'clock, there's a point associated with that. And over here on the vertical axis, it looks like it might be about 32. So I'm going to write down 32 underneath T2. And then for T4, I have a point that seems to be just a little bit above 25. It might be 25.5, it could be 25, it could be 26. It's just an approximation, but regardless of that approximation, it is clear that T2 is going to be larger than T of 4. So let's look at part C. So in part C, we're going to be thinking about this mapping in reverse. So typically when we think about a map, let me make the arrow map representation here. We would normally pick something over here. For example, if we pick 1, we know that 1 is going to map to 27. We came up with that in part A. But what I'm asking for here in part C is, what is the x value that's going to end up mapping to 25? So rather than picking something from the first set to calculate something in the second set, I already know what I want from the second set. I have to figure out what from the first set is going to provide that value. So the approach that I'm going to take here, let me erase some of the things that are already on the graph just so we can clean it up a bit. I'm going to come over here to the vertical axis at 25, and I'm going to mark this horizontal line going all the way across my graph. And I should find that there are 2 places where that horizontal line crosses the curve. Sometimes you may only have 1. Sometimes you'll have more than 1. This one happens to have more than 1. And then I can take each one of these points and I can translate them down to the horizontal axis, and I can check to see what is going to be the x value that I can associate with each one of those points. And that's going to give us our solution. After all, it does say solve the equation. T of x is equal to 25. So I can write this in one of 2 ways. The first way is going to be using the approximation symbol. I'm going to say x is approximately. And for the first point on the left, it looks like it might be about 0.7, which I know that you would translate to be around 1240, 1245. But here we're talking about going between 0 and 1. And then for the second point, the one the furthest to the right, I would say that's about 4.1. So that would be one way to write this. Or for those that want to use the curly bracket notation, which is another way to write a solution set, we can just open up a curly bracket and then make a list of our solutions that way. So that would be one of 2 ways that we could do that. All right, and the last part, part D, wants us to build on part C. So it does say T of x equal to 25, which we already know. We've already marked those points. But we also want to mark all the points where we are going to be greater than 25. So what points are we going to see have a temperature that's greater than 25? Well, any point that's going to be above my horizontal red line here should have a temperature that's greater than 25. So starting at the left point, I'm going to now trace all of the ordered pair, all these points in between, until I get back to that horizontal line. So everything that I've highlighted in red just now represents a point where the temperature is greater than 25, and then the endpoints represent where we are equal to 25. So that means that there is a infinite number of x values that I would have to represent. So translating all of those points down to the horizontal axis would look like this, starting at 0.7, and then I'd have to account for everything all the way until I get to 4.1, and that looks like an interval. So we're not going to list the answers for this. That would be impossible. There's just too many to do that with. So this is where we're going to use interval notation again. We can use interval notation to say that the x values that we want are going to start at 0.7, and it's going to be all of the numbers in between until we get to 4.1. And then that would represent the solution set.